Welcome everyone to 11.6 absolute convergence and the ratio test. Now in this section we're going to expand on what we did in 11.5, which was alternating series. We're going to talk a little bit, okay, so if you have alternating series, maybe this thing converges, but maybe it absolutely converges. So that's a new idea. We'll go over a definition of that. We're going to understand this ratio test, which is the new test, and it's probably everyone's favorite from chapter 11. And then finally, we'll actually apply it to a few things. So let's get started with the definition. So here, definition 11.6.1 says we have our series. So this is a summation of a sub n's is called absolutely convergent if the series of absolute values, so now we have the sum of absolute value of the terms, is convergent. So it kind of makes sense, absolutely convergent. All right, the next definition we have a series, again, a sub n's, are called conditionally convergent if it is convergent but not absolutely convergent. So there are two definitions. So let's go ahead and try to use these to show that our series here is conditionally convergent. So we have the sum and we have -1 to the n over n. So the first thing I want to say is that this series right here is indeed convergent. Why is it convergent? Well, it's because of the alternating series test. Right, so the alternating series test says, well, first of all, the limit of the absolute values has to go to 0. That's check, right, because 1 over n goes to 0. And then also we have decreasing absolute value terms, and that also is true. So yes, this indeed head towards 0. Great, alternating series test, convergent. However, when I take the absolute value of this thing, right, so the absolute value of these terms, we get 1 over n. And we know that this sum of 1 over n is divergent. Why is that divergent? Well, it's because of the p-series test, right? So one of the very first things we learned, the p-series test says if p is less than or equal to 1, it's divergent, right? So therefore, the summation of the -1 to the n over n is conditionally convergent. Again, it's convergent, but it's not absolutely convergent. Okay, so why do we care about absolute convergence? Well, if a series is absolutely convergent, then it is convergent. So in some sense, absolutely convergent is a stronger condition, right? Everything that's absolutely convergent is then convergent itself. So if you can prove something is absolutely convergent, you've proven that it's convergent. All right, let's do this example here. Determine if the following series is absolutely or conditionally convergent. So let's go ahead and look at the absolute value of our terms. Well, with this, the -1s, as they alternate back and forth, those would always just be positive. So essentially I have 1 over n squared. Remember, n is a natural number, so that's positive. Well, what do you think about this? Does this converge? The sum of 1 over n squared from n equals 1 to infinity? Yes, absolutely. So it is convergent. Why is it convergent? Again, we're justifying our work here. That's because of the p-series test. Again, p-series test says if we're greater than 1, right, 1 over n to the p is greater than 1, that p is greater than 1, then great, you have convergent. So, yes, we have that our series, the sum from n equals 1 to infinity of -1 to the n plus 1 over n squared is absolutely convergent, right? So we look at the absolute value of the terms, see is this convergent or not? Great, it is, so it's absolutely convergent. All right, let's get to the ratio test here. The ratio test, we're looking at a limit here. Limit as n goes to infinity of a ratio of our terms. And we're doing the a sub n plus 1s, so the n plus 1 term, and then over a sub n. Now, if this equals L and L is less than 1, then the claim is our series. And notice that this doesn't have anything about positive term values or anything. It can be an alternating series, whatever. Works on everything. Then the series is absolutely convergent. So the ratio test is very powerful. And because it's absolutely convergent, we know that it is therefore convergent. Now, if this limit, L, is greater than 1, or the limit's equal to infinity, then our series is divergent. And then finally, if this limit of the absolute value of the ratio is equal to 1, then the ratio test is inconclusive. And that is that we can make no conclusion one way or another, right? No conclusion can be drawn about the convergence or divergence of our series. So let's go ahead and try to apply this, the ratio test, to a few things here. So I have an a and a b. What happens if I try to apply the ratio test to the sum of 1 over n as n goes from 1 to infinity? Okay, so we're going to look at this limit, a sub n plus 1 over a sub n, the absolute value of this. So a sub n, well, that's just 1 over n, right, when I plug in n. And now a sub n plus 1, well, I would plug in n plus 1 everywhere I see an n. So I have this 1 over n plus 1. Now let's go ahead and simplify this down a little bit with some algebra, right? When we have all this division, instead of dividing by a fraction, I can multiply by its reciprocal. So I'm going to multiply by n over 1. And in fact, let's clean this up a little bit. We know 1 times n is just n. And so there we go. Now I have a relatively clean looking thing, n over n plus 1. And if we remember our Calc 1, right, about horizontal asymptotes, we know that this goes to 1. Or if you'd like, you can apply L'Hopital's rule. So in this case, the ratio test says we know nothing. So the ratio test is inconclusive because this limit is equal to 1. However, we know that this series is in fact divergent. So this series diverges. Why do we know this? Well, it's because of the p-series test, right? P is equal to 1 in this case, so therefore it diverges. But the ratio test doesn't know that, right? Okay, part B, let's try this one out. So our series is now 1 over n squared as n goes from 1 to infinity. Let me see, what does the ratio test tell us about this? So we have the limit as n goes to infinity of the absolute value of the ratio. So again, a sub n is going to be 1 over n squared. A sub n plus 1 is going to be 1 over n plus 1 quantity squared. And again, let's go ahead and simplify this with a little bit of algebra. Instead of dividing by a fraction, let's go ahead and multiply by the reciprocal. So I'm going to multiply by n squared over 1. And again, let's clean this up a little bit, because I know 1 times n squared is just n squared. And then what does this head towards? Well, again, we remember our Calc 1, which would say 1 here. Or you can use L'Hopital's rule, whichever you're comfortable with. And either way, you get the number 1. So now I'm going to use the magic of technology here, because the ratio test is going to say essentially the same thing, right? The ratio test is, again, inconclusive, because this limit was equal to 1. However, we know 1 over n squared actually converges, this time by the p-series test. So the big thing is that when this limit is equal to 1, sometimes it'll converge, sometimes it will diverge, and the claim is the ratio test knows nothing. It is, in fact, inconclusive. Okay, so I've shown you a couple ways on how the ratio test can't be used, unfortunately. But let's figure out a couple ways where it can be used. So I wanted to recall that n factorial, right, n with this exclamation point, is the product of the first n whole numbers, or natural numbers. So n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. So the example I give here is 5 factorial is 5 times 4 times 3 times 2 times 1. Right, so it's the product of the first 5 natural numbers. So one interesting thing, though, is that you can often rewrite this as, 5 factorial is the same as 5 times 4 factorial, right? Because 4 times 3 times 2 times 1 is 4 factorial. So 5 factorial is equal to 5 times 4 factorial. So this is an interesting tidbit of information right here. We will see how this is used in this upcoming example. Okay, so I have a complicated series here. 2n factorial over n factorial squared, and now I need to determine if this thing converges or diverges. And so I'm going to try to apply the ratio test. So I'm going to write down my a sub n plus 1. So everywhere I see an n, I'm going to plug in an n plus 1. Check. And then I'm going to divide that by a sub n. So that's just my terms here. And yep, there's my a sub n plus 1. Here's my a sub n, and I've divided these things. Because it's so big, I decided to use a different division sign. So again, instead of dividing, let's go ahead and multiply by the reciprocal of an. So again, and I'm going to go ahead and distribute here as well. So 2n plus 2 factorial over n plus 1 factorial times n plus 1 factorial. That's the same thing as n plus 1 factorial squared, times n factorial times n factorial, that's the same thing as n factorial squared, divided by 2n factorial. Okay, and the idea is that I want to group a few things together. So let's go ahead and I'm going to do the limit as n goes to infinity, and I'm going to first look at this n factorial divided by n plus 1 factorial. n factorial divided by n plus 1 factorial. But instead of n plus 1 factorial, let me go ahead and expand this out. This is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Now this part right here, well, that's the same as n factorial. This is n times n minus 1 times all the way down to 3 times 2 times 1. That's n factorial. So I can rewrite this. Instead of n plus 1 factorial, I can write it as n plus 1 times n factorial. Why would I want to do such a thing, right? And this is definitely related to the example up here. 5 factorial is equal to 5 times 4 factorial, right? Why would I want to do this? Well, it's because I can now cancel my n factorials. So you can see that this is the same thing as just 1 over n plus 1. We can pull off the same trick with the other n factorial and n plus 1 factorial. So let's go ahead and do it. Cancel this stuff out. And again, I have another 1 over n plus 1. And then finally, let's go ahead and group and think about this 2n plus 2 factorial over 2n factorial. So 2n plus 2, this is and then 2n plus 1, and then 2n, and then 2n minus 1, and then 2n minus 2, and then all the way down to 3 times 2 times 1. And then at the bottom we have 2n factorial. And now if we group all of this stuff together, we can see that it's the same as 2n factorial. It's the product all the way up to 2n. So in fact, this is the same thing as 2n plus 2 times 2n plus 1 times 2n factorial. These things cancel, and there we are. So now we've simplified this quite a lot. We've gotten rid of all of our factorials, and the only thing we have here, we have the 2n plus 2 times 2n plus 1 over n plus 1 times n plus 1. And there are quite a few ways that we can go ahead and evaluate this limit. We could use L'Hopital's. We could expand it out, all this good stuff. I'm going to go ahead and expand things out a little bit and do some algebraic cancellation and whatnot. So we have 4n squared plus 6n plus 2. So that's if I were to expand out the top. And then in the denominator, we have n squared plus 2n plus 1, if I was to expand this out. And if I use L'Hopital's rule here, well, take the derivative of the top, take the derivative of the bottom, right? Because both this is an indeterminate form, infinity over infinity. I would get 8n plus 6 over 2n plus 2. Okay, well, this is still an indeterminate form, infinity over infinity, so let's use L'Hopital's rule again. And that's going to give me, let's see, a nice 8 over 2. Well, that doesn't have any more n's in it, so that's just going towards 4. So according to this up here, we're in case 2. Case 2 says, well, this is divergent. We have a divergent series here. So by the ratio test, our series, which was the sum from probably n equals 1 to infinity of 2n factorial over n factorial squared, is divergent. And this is the sort of work I would expect you to show, right? You always have to state which test you're using. So, hey, I'm using the ratio test. All right, and with that, we're all done with this video. You can see this example is pretty tough, but this is a classic example of how the ratio test gets applied. So go ahead, take a break, and when you're ready, come back for the second video. I'll see you shortly.